All right, so we are going to be reviewing respiratory system. So let's get started, shall we? Okay, so this guided tour will be hopefully only 10 minutes. So let's get started as we move on to the next slide. Let's get back to. So hopefully within the next 10 minutes, you will learn about how our respiratory system works. So let's keep moving. The first thing that we see here is basically the lungs. These are our main players in the respiratory system. I wanted to point out that you have three lobes. So three lobes on the right side and only two lobes on the left side. This is a three-dimensional view of your lobes, left versus right lung. All right, so let's move over here and you're going to see that we have the nasal cavity with the nasal concha, and watch my arrow. Right in here is the oral cavity. So when you're breathing in the air, it's coming in through the nostril, through the nasal concha, down the pharynx, into the larynx, trachea, and then right and left bronchus, into the branches, and eventually to these air sacs called alveoli. So the alveoli is where all the gas exchange takes place, and we discussed during cardiovascular system that gas exchange occurs at the alveolar level because the capillaries are exchanging CO2 for O2 as we go down the partial pressure gradient of CO2, which is higher at the capillary level from that pulmonary arterial side, and lower at the alveolar level. So obviously CO2 diffuses across to the alveolar sacs. And then the alveolar sacs, since you already picked up a lot of oxygen on that inspiration or the inspirational ventilation process of inhaling, there's a lot higher pressure on the alveolar side, and it diffuses down that partial pressure gradient from higher pressure in the alveoli to a lower pressure of oxygen at the capillary level. So the capillaries are picking up all this oxygen, but what's in the capillaries? Red blood cells, and the red blood cells carry a lot of hemoglobin. How much? 4 million hemoglobin molecules, and all of those 4 million hemoglobin molecules have 4 binding sites for oxygen. So even just one red blood cell is going to pick up 4 million oxygens. Multiply that by 4, that's 16 million ways that one red blood cell can pick up oxygen. So how amazing is that? So at that level, we are picking up oxygen. And we are now going to that venule side, which, because it's the pulmonary circuit, it's a short circuit. We know that the veins do the opposite of what happens in the systemic circulation. The veins, yes, they're bringing blood back to the heart, but they're bringing back oxygenated blood. Unlike the systemic circulation, we're bringing back freshly oxygenated blood from the lungs to that left side of the heart via the left atrium and ventricle. So key elements to remember here is that we have 3 lobes on the right lung, 2 lobes on the left lung, and that we have the diaphragm. And this diaphragm, we're going to show you very soon how it moves downward as the lungs expand. So basically what you need to remember is that the airways are going to be bringing the oxygen to the lungs. The pulmonary arteries are bringing deoxygenated blood from the right side of the heart. And the pulmonary veins, 2 from the left and 2 from the right, are bringing freshly oxygenated blood from the alveoli to the capillaries, from the capillaries to the pulmonary venules and pulmonary veins. 2 from the left lungs, 2 from the right lung, entering that left atrium and ventricle. So the pulmonary circulation, as you know, is low pressure, high volume, because we're returning this deoxygenated blood back to that right side of the heart, and of course to the lungs. The pulmonary arteries will deliver that systemic venous blood to the lungs, and so the branches that profusely spread out across the bronchi are going to feed all that deoxygenated blood to all the capillary networks, and then of course exchange the CO2 for oxygen, and the pulmonary veins are going to carry the oxygenated blood from the respiratory zone to the left side of the heart. So basically, the four mechanical and physiological processes is the key elements of what I need you to remember. One is pulmonary ventilation. We're going to learn about pulmonary ventilation right now. Two is the external respiratory process, which I started to describe a little bit just now, where oxygen is exchanged for CO2 so that on the exhale, you're exhaling out the CO2, but on the inhale, you're picking up the O2, and it's all because of that relationship between the alveoli and the capillaries. Third part is the actual transportation of that oxygen and CO2, so we're going to discuss that for a little bit. And then the fourth part is internal respiration at the cellular level, the exchange of oxygen and CO2, where now it's the reverse of what you saw in the lungs. Now you are going to diffuse across from the capillary side to the cellular side, to the cells of the tissue, picking up the O2, and the cells are going to build up CO2 from their metabolic processes. So that's going to be moving via diffusion from the cellular membranes to the actual capillaries. And of course, CO2 has multiple ways of transporting it back into the respiratory system via the circulatory system. So as you can see, the circulatory system, the vascular system is interrelated very much so with the respiratory. So respiratory and vascular are interdependent with each other because of these four basic, very important processes, which we're going to discuss at length now. All right, so let's go on to the next one. Now let me clear all these annotations and remove my annotation. Let's see, erase, undo. And unfortunately, this is where I always get stuck. Okay, now let's see if I can move to the next slide. Okay, so I just had it to remove the annotation to be able to work that through. Okay, so now that you understand that, we are going to move on to the next slide. And here, I'm going to reuse the annotation, and then I have to remove it so that I'm able to move through these slides. Okay, so the major process is that the four processes include ventilation, external respiration, transport of gases, and internal respiration. Okay, so that is the gist of my lecture today. We are going to go over ventilation, external respiration, transport of gases, and internal respiration. Once you understand these concepts, then I will present to you a different PowerPoint presentation that is going to help you understand a lot of what I'm talking about in terms of the details of how we bring in all this oxygen and how we can actually measure it. Okay, so let me clear all these annotations. And here we go. And it's fun using the annotations, but I also have to remind myself when to clear it out. Okay, so the mechanism of breathing, it all starts in the ventilation process. So ventilation is the first of the four processes that I was discussing. All right, so process number one is the movement of air entering the trachea to the right and to the left bronchi, and then to the bronchioles, and then eventually to the terminal branches with all those alveoli. And these are the alveoli, as I showed you earlier. Pretty cool little lab model here. Now, the actions are responsible for air movement. The action responsible for air moving in, I should say, is inhaling. That's the layman term, but we're going to say inspiration. So that's the term, inspiration. And your external intercostal muscles between your rib cage, between your ribs, are going to allow the rib cage to lift up and expand all the way. Even the clavicle and even your scalenes in your neck muscles are going to allow the lifting up so that even the apex of your lungs can expand. So that's what inspiration is, okay? So let's go on to the next slide and show you. Let me move it over here and let me move this over there. Okay, so now that I have my little box in the corner, you can see the imagery. So let me annotate again. I'm going to talk about inspiration and expiration. So inspiration, we're going to go from a higher atmospheric pressure outside, okay, to a lower pressure inside the lungs, which we call P-pull, pulmonary pressure. So this is the shorthand that we describe. So this is the pressure in the lungs. This is the pressure in the lungs. And so we want to go down the partial pressure gradient from a higher pressure outside to a lower pressure inside. So if we go down the pressure gradient, it's like rolling the ball down a hill. We're going down the gradient, so there's no effort. So air moves down the pressure gradient. It always allows the air is always allowed to move in from an area of high pressure to a low pressure down that pressure gradient. The gradient is therefore the difference between the PATM and the P-pull, okay? And so what I want to say is this. Let me clear all drawings here and let me do this. Boyles Law boils down to, haha, no pun intended. I know that was a mom joke. Boils down to that is pressure. The law of pressure and volume are inversely proportional. So Boyles law in physics describes that pressure is inversely proportional to volume. So as the pressure goes down, volume goes up. So when these lungs expand, the volume of the lungs expands, the space there expands, the space inside the lungs expands, so P-pull goes down. As the volume goes up, P-pull goes down. Why? Think of it as going into an elevator. If you are the only one in the elevator, it's just you. Think of you as that oxygen. There's not a lot of oxygen around me, it's just me. Okay, so there's plenty of volume around me and there's not a lot of pressure. Okay, so that is why air naturally flows in and oxygen flows into the lungs. Okay, based on Boyles law. So Boyles law states that pressure is inversely proportional to volume. So as the lungs expand, volume goes up and pressure goes down. The diaphragm drops down and the arrows representing expansion looks like this. Okay, so that's inspiration. Now let me clear all these annotations and let's move to expiration. So in expiration, the lungs are recoiling back to their natural state. So the pressure goes up because there's less space. If there's less space, there's less volume, right? So these are the arrows representing the lungs recoiling, right? So that's what we see here. Lungs are recoiling. So pressure goes up, volume goes down, and that's because now think of it as there's a lot of CO2 in this elevator and they want to get the heck out. So they're going to go out because P-pull, meaning the pressure inside the lungs, is greater than PATM, the pressure outside the lungs, which is the atmospheric. All right. So here, PATM, meaning atmospheric pressure, is greater than P-pull. meaning the pressure in here. Why? Because volume is going up and pressure goes down, right? Here, pressure is down, volume is up. Here, pressure is up, volume is down. Lungs are recoiling. Here, P ATM is less than P pull. So we go down the partial pressure gradient, down the gradient from higher pressure inside to lower pressure outside. Okay, so that's how that works. So I hope that helped a lot. Let me just clear all the drawings. Let me remove the bar so that I can move on to the next slide. Okay, so now all of this is also related to the pressure between the lung and the cavity. So the cavity itself, okay, is the left and the right pleural cavity. And the lining that covers the cavity, okay, is called the parietal pleura, and it lines the cavity, okay? And so let me draw that out for you. It lines the cavity. Now listen, in between, we have this little space here. I don't know if you can see my drawing, but that little space is the space in between the lung and the cavity. So we call this PIP, which is basically the intrapleural pressure. So we can measure the PIP, the pleural pressure inside in the intrapleural space. It's the space between the lungs and the cavity. Now, also to note, let me draw this in a different color. The visceral pleura is the lining directly on the lungs, as you can see here. I've had a lot of coffee, so forgive me if it's not perfectly straight. So that is the visceral pleura. Okay, now I want to tell you about PIP, so important. This pressure always, always, always must be lower than P pull. Let me draw this in red. Okay, so even if the pressure in here is the same as P pull, if this pressure increases to equal or greater than P pull, the lungs collapse. You do not want to have any high pressure here. That is why the lung is in a vacuum, so that there is no air. But if you puncture and cause a puncture through an injury, okay, a thoracic puncture via like let's say a stab wound, okay, now blood can enter in this pleural space, all right, in the pleural cavity between the parietal and the visceral pleura, and this blood is going to increase PIP. And if PIP is equal to or greater than P pull, then we have a problem. The lungs collapse. So I wanted to point that out to you because that is super important, especially if some of you are going into the clinical world as healthcare professionals. All right, so let's look at the slide here, what it says. Basically, the visceral and the parietal pleura play a role in ventilation. Double-layered serosa, the parietal pleura is on the thoracic wall, and it also faces the superior surface of the diaphragm. The visceral pleura is directly on the lung surface, and the pleural fluid fills the slit-like pleural cavity, and we don't want high pressure there because if it's equal to or greater than, the lungs will collapse. And then, just so you know, the pleural fluid is going to decrease surface tension and allow for lubrication. All right, so let me clear all annotations and get rid of that bar. And now we can move to the next slide. So in this slide, I am showing you that the transpulmonary pressure is super important. We don't want this number here, the intrapleural pressure, to ever be equal to or greater than the pressure in here. Now, when you're inhaling, obviously the pressure diminishes and the volume increases. When you're exhaling, the pressure changes in the lungs, people. okay? But by the way, at the top, when you take that deep breath all the way at the top, now P pull equals PATM for a brief moment in time. And then on expiration, your lungs recoil, your pressure goes up, and your volume goes down. So just so you know that in the pressure in the lungs, the P pull changes with inspiration and expiration for obvious reasons, as I said before, because we expand the lungs and the volume goes up, pressure goes down, air flows in, inspiration. So now the pressure goes down in here on inspiration. And then when you inhale all the way to the top, the apex of your lung, now the pressure inside right now at the top of my breath equals the outside pressure, the atmospheric pressure. We can't stay there. The lungs naturally need to recoil. So the lungs recoil, pressure goes up, volume goes down, pressure changes in here, it goes up, okay? Bottom line, this pleural pressure must always be a negative number. It must always be less than the P pull, okay? If it's equal to or greater than, this pressure is going to cause collapse of the lung. Okay, so let me clear all annotations, get rid of that, and we move on to the next slide. And I actually have this right in here to demonstrate inspiration and expiration. So I'm going to hold the top, and on inspiration, the diaphragm, and I'm not as strong as I look. There it is. See that? As the diaphragm drops, I don't know if you can see this, but the lungs expand. And then as the diaphragm returns to normal, the lungs retract, pressure goes up. So this is Boyles Law. Boyles Law, let me do the annotation again. Bottom line is pressure goes up, volume goes down, pressure goes down, volume goes up. So let me ask you, when pressure goes up, volume goes down, what process is that? That process is right here, expiration. When the diaphragm goes back to its original dome shape and the lung recoils back to its original shape. Okay, so diaphragm goes back to dome shape. Here, pressure goes down, volume goes up as the lungs expand. So air flows in, diaphragm drops. So I hope this is super clear for everyone. Boyles Law, pressure is inversely proportional to volume. Lungs expand, volume goes up, pressure goes down. Consequently, as pressure goes down inside the lungs, P pull is greater than PATM, so air flows in with oxygen going down the pressure gradient from higher PATM to lower P pull, and so the lungs expand as the diaphragm drops to allow full expansion and volume of lung inflation. On the flip side over here, this is expiration. So now we have the opposite, okay? We have the opposite where pressure goes up and volume goes down. Dome shape, return of dome shape to the diaphragm, lungs recoil. And as lungs recoil, you can see the volume goes down and pressure goes up. So hopefully this was super, super clear to you. Let me clear the annotations now and move on to the next slide. So this slide really shows it nicely. I hope this helps you. This sequence of events of inspiration is great. I like this image a lot. It works very well in understanding the inspiratory muscles, including your diaphragm, which is a muscle. The diaphragm drops down. In is X, X is in. This is how I remember it. On inspiration, it's the external intercostals contracting. And what happens is your whole rib cage, ribs elevate, sternum elevate, your clavicle is elevated due to your anterior, middle, and posterior scalenes. if you remember that from A&P1. And so the inspiratory muscles will help in this lifting. The diaphragm descends, the rib cage rises, the thoracic cavity increases, the volume of the lungs increase, the lungs stretch, the intrapulmonary volume increases, and the pressure drops to a -1 millimeter mercury. Air flows in, and we go down the pressure gradient. Air goes from higher pressure outside, oxygen goes from higher pressure outside to lower pressure inside, down that concentration gradient of gas, down that pressure gradient of gas, and air flows in. All right. So that is pretty much what happens on inspiration. Whoops. Now on expiration, let's do the next one. On expiration, this is what we have. We have the reverting back to the original, right? So we have the diaphragm returning back to its dome shape. So diaphragm returning to its dome shape. The rib cage drops back down, so the rib cage descends due to recoil of the costal cartilages. Your external intercostal muscles relax. Your thoracic volume diminishes, the lung volume diminishes, and the elastic recoil of the lungs occurs, thereby increasing the pressure to a +1 millimeter of mercury. So now air flows out down that pressure gradient until the intrapulmonary pressure is 0. And the pressure is always 0 between the breaths. So as I take my deep breath, I'm going to stand up and I'm going to expand. My diaphragm drops, deep diaphragmatic breathing, inhale, all the way up to the clavicle. And now pressure inside my lungs equal the pressure outside, just temporarily. And now very slowly exhaling out through the nose, the pressure increases, the volume decreases. Okay, so that's pretty much the ventilation cycle. So I do hope this helped. As I move on to the next slide, let me clear the annotations. All right. So bottom line is, what do we need to know? Here we go. We need to know that on inspiration, we have the external intercostals contract, but on expiration, the external intercostals relax, and the internal intercostals will contract to bring the rib cage back down. The diaphragm contracts and drops down, descends, and there's a decrease in space in the abdominal content because of that diaphragm dropping. That's what diaphragmatic breath is. And so it allows for a full expansion of the lungs in the thoracic cavity. In expiration, the diaphragm relaxes and returns to its dome shape. In inspiration, the volume increases. In expiration, the volume decreases. In inspiration, the pressure goes down, right, because of that lung expansion, Boyles Law. In expiration, the volume decreases because the lungs are recoiling, so the pressure goes back up. So therefore, down the partial pressure gradient from a higher P pull is greater than PATM, which means that the pulmonary pressure is greater than the atmospheric pressure. Whereas here, P pull is less than PATM. So therefore, air flows in. O2 in. Air flows out, meaning O2 out. CO2 out, pardon me. CO2 out. All right, so let me clear this and move on to the next slide. So again, to review, annotate, Boyles Law, super important in understanding. During inhalation, the rib cage expands. As the rib cage contract external intercostals, look at this diaphragm. It moves downward, okay? Air flows toward the lower pressure inside the lungs. All right, super clear. So I'm going to move on to the next slide. And during exhalation, we have the lung volume diminish because the lungs are recoiling back to the original position, dome shape, meaning the diaphragm goes back to the original dome shape. Pressure increases, air flows from higher pressure inside the lungs to outside the lungs. All right, now we go on to our second process. The first process we talked about was ventilation. The second process we're talking about is gas exchange at the alveolar level. So air flows in, as you remember, and brings in oxygen. But we also have to take into account the deoxygenated blood that is coming from the right side of the heart. If you remember the heart, you had the right atrium and the right ventricle, and you had that pulmonary trunk. And that pulmonary trunk led to the right and left pulmonary artery. And if you remember, I should draw it in blue because it was deoxygenated blood. And so deoxygenated blood is coming in like so. And so we've got all these red blood cells filled with CO2 in the form of bicarbonate, also bound to hemoglobin as well. Basically bound to hemoglobin as carboxyhemoglobin. All right, so what happens is that we're dumping the CO2. Why? Because on this side, the PCO2 is low, but the PO2 is high. So let me draw this in red. PO2 is high. So therefore, oxygen comes in from high concentration to low concentration, and CO2 goes out from high concentration here to low concentration here. Okay, and so we always focus on the gradient, and in this case, it's the gradient of these gases, the CO2 and the O2. Follow the gradient from high to low, just like rolling the ball down the hill. Okay, all right, so let me clear all annotations, and now we move on to the next slide. And this basically shows you the importance of PO2 of venous blood in the pulmonary arteries is only about 40 millimeters of mercury, as opposed to the PO2, which is approximately 104 millimeters of mercury measurement in terms of pressure in the alveoli. This steep oxygen partial pressure gradient will allow the easy diffusion from higher concentration to lower concentration down that gradient into that pulmonary capillary bed to bring that blood to that left side of the heart, left atrium, left ventricle, to the aorta, and throughout the rest of the body. For that last portion that we're going to discuss, the understanding of the transportation, which is the third portion of our discussion, and of course the delivery of that oxygenated blood to the tissue. Perfusion is what we call it. All right, so let's clear this out now and let's move on to gas exchange. As you can see, external respiration is what we just mentioned. All right, so we mentioned ventilation was part one. External respiration is part two, where we have the exchange of CO2 for O2. So now we got the O2 flowing into the blood. The next thing that we're going to talk about, let me just move my bar. The next thing we're going to talk about is right here, perfusion. And that's the last portion, the transportation of that oxygenated blood via the systemic vessels, the arteries, and then final perfusion to the cells. And so the flow of air from the external environment happens due to pressure changes in the lungs. The alveolar gas exchange is the surface area, the partial pressure gradient of gases, matching ventilation and perfusion. But once we get this O2, we need to get to that final stage, transportation, and then moving and transferring out. Internal respiration is the process, moving and diffusing across our alveoli to the cells, oxygen, and from the cells to, what did I just say? Alveoli, pardon my French. Made a mistake. Internal respiration is the movement of that oxygenated blood from the red blood cells to the cells, the tissues, and the cells within these tissues. And our cells and our tissues produce CO2, so that's going to be picked up by the capillaries. And now the red blood cells are going to be deoxygenated, and the blood itself, the plasma, is also going to carry out the bicarbonate and bring that deoxygenated blood back via the systemic venous system. And so systemic venous circulation. So the last portion is transportation and internal respiration. So to recap, we had ventilation, we had external respiration, we have transportation of that oxygenated blood to the tissue, and then internal respiration. All right, so let me continue on to our next slide. Oh, I didn't remove my annotations. When I forget that, it shows up on my next slide. All right, here we go. And let me move my bar. Okay, so we are at the halfway mark, and we are going to go over what we need to go over one more time. So we have transportation, that's all that's left, and internal respiration. So hopefully you understand ventilation and you understand external respiration, which is basically O2 is exchanged for CO2. So the exchange between the lungs and the blood at the capillary level, and bringing that oxygenated blood via the pulmonary veins to the left side of the heart, left atrium ventricle, aorta, and throughout the rest of the body systemically. And we get to this part right here, transportation via the systemic arteries, arterioles, and finally at the capillary level, we are exchanging the CO2 that's built up in the cells, and that diffuses across, and that's why we have internal respiration. And the O2 is going to be transported to the cells, and that's internal respiration. O2 and CO2 is exchanged between the systemic blood vessels at the capillary level and the tissue. So what you're looking at here is that the red blood cells carry oxygen in your hemoglobin molecules. Here's a hemoglobin molecule with the iron, the 4 iron sites, and the binding sites are 4 binding sites for oxygen. The carbon dioxide, which is transported in the blood, is going to be brought back via the venous system. It's either dissolved CO2 or CO2 bound to hemoglobin or bicarbonate, which can easily convert to a gas, CO2, at the alveolar level. So this is the next and final portion of our discussion, gas exchange, where oxygen and carbon dioxide are transported by the blood. So the cell, what's it going to get rid of? It's going to get rid of the CO2. And what is it going to need? It's going to need oxygen. It's going down again, that gradient from a higher concentration outside to a lower concentration inside the cell. All right, let me clear my annotations and we move on. And so this is the third process, transportation of the oxygen and the CO2. Carbon dioxide is transported in the blood via dissolved CO2, CO2 bound to hemoglobin, and bicarbonate. And this just shows you the red blood cells that are transporting the hemoglobin in the form of iron, its basic structure, and the 4 binding sites for oxygen. And don't forget, we have 4 million of these hemoglobin molecules in one red blood cell, and each of those 4 million have 4 binding sites. So that's 16 million ways that we can pick up oxygen. All right, so the last process is internal respiration. And this is where the cells of the body are going to accumulate CO2, so that diffuses across from a higher concentration of CO2 here to a lower concentration of CO2 here. So therefore, we go down that concentration gradient. Here we have a higher O2 level, and so we go down the concentration gradient. So the exchange of gases at the cellular level is what internal respiration is. It's between the tissue and the cells and the blood in the systemic capillaries. All right. So this is my slide where I'm going to insert this actual video presentation that I'm doing now. So pretty redundant, but I will put it in, and so you can go back and just review so you have a narrated PowerPoint. All right, so clinical impacts, I'm almost done. I just did want to show you that ventilation is super important. And what are the three major factors that increase resistance to airflow? Well, if the diameter of the bronchioles are smaller or constricted, less air flows in. So that's very important. Also, the elasticity of the chest wall and the lungs so that air can come in. That's super important. And then in specific diseases, collapse of the alveoli. These air sacs are their own function. Their only thing in life is to pick up oxygen and to get rid of alveoli. So the more collapsed alveoli we have, the increased COPD we have, and eventual failure of the respiratory system. All right, so basically I'm going to give you one example and then we'll end this presentation. Let's show you. Asthma. So asthma is where we have the bronchial constriction, and we also have bronchial edema with mucus plugging up so less air can flow in. So that is a huge problem, and therefore all four sites are going to be a problem: ventilation, external respiration, less transportation of oxygen, and less internal respiration, which creates a problem. Not all the tissues are getting enough oxygen, and that is a huge issue. All right, so I wanted to show you that before we end our presentation. And our ending is a little teaser for our next session, part 2, which is a preview below. So what we will be discussing is respiratory volumes and capacities. So me breathing in and out at rest, in and out at rest is tidal volume. Me taking a deep breath as if I'm ready to jump in the water. So a regular breath, suck in more, suck in more. Now you got your inspiratory reserve volume. Okay, so that's number 2, inspiratory reserve volume. Now, expiratory reserve volume is inhale, exhale, and now you're exhaling more than what you normally exhale out. So kind of like when you're lifting weights and you're taking that deep grunt, right? And then residual volume means that you still have some air in your lungs even after your normal tidal volume, or even after you do your inspiratory and expiratory reserve volume. And then what we do is we take all these numbers and we add it up. So we add up inspiratory capacity. Sorry, I'm tongue-tied. Tidal volume is your regular in and out breath during rest. And what is your inspiratory reserve volume? So that's inspiratory capacity. Functional residual capacity is your expiratory reserve volume, what you release on that deep exhale, plus your regular residual volume that's left over. Your vital capacity is adding normal in and out breathing, inspiratory reserve volume, expiratory reserve volume. And then what we can check out how we are doing is total lung capacity, which is adding up tidal volume plus inspiratory reserve volume plus expiratory reserve volume plus residual volume. Okay, and please note, we females are different. Yes, we are. The numbers are different. The numbers are greater in the males, just FYI, probably due to size. And here's my lungs to demonstrate. And you can see that I have lots of lab models here, and I'm going to create a new YouTube separately just for that. All right, so I do hope you enjoyed this lecture. I know I way went over 10 minutes. Oh, well, but at least I know that you guys hopefully understand introductory, just introductory, part 1 respiratory system. All right. All right. So I think I'm going to stop recording now and say bye to you all. Bye.